In yesterday's lecture, we learned that a piezoelectric sensor generates a current that is proportional to the rate of change of the applied strain. Just as a quick reminder, we developed the equations I is equal to SCV plus SE33 A3 S3 for a longitudinal, and I was equal to SCV plus SE31 A3 S1 for a transverse configuration. And this variable S is effectively our rate of change quantity. Okay. So I'm calling it a rate of change quantity because it's a natural frequency. So it's something measured in per seconds, which is to me a rate of change. Okay. So we can see that our signal is proportional to S, as specifically over here in the portion of our current that is dependent on the piezoelectric properties. We also have a linear proportionality with S, or linear proportionality with our rate of change. Okay. So this current is typically extremely small, on the order of picoamperes in size. And so we, typically speaking, need to use amplifiers in our measurement schemes. Okay. So one way that this is carried out, let me put this down here, is a current measurement scheme, is through the use of what's called a transimpedance amplifier. So if we have our piezo element, and I'm just going to literally draw that as a simple box here. One leg of this guy is grounded, and then the other leg of this guy is connected to our amplifier system. So I'm just going to have a simple op-amp based circuit here. Utilizing negative feedback. So here I've got some feedback resistance R, and here I have some capacitance C. I'm going to have an output voltage here. So this is my effectively processed and amplified signal. And then the signal from the piezo element is going to be our current I, and we're going to say that it is approximately going to be the motional part of our current. So we're only interested effectively in the part that is related to the piezoelectric effect. Okay. So the reason why we're only concerned with that motional current has to do with the way that we have connected things. So for those of you that don't have a particularly strong electrical background, this might be a little hand wavy or magical, but this is how op amps work. Generally speaking, so in a negative feedback configuration, almost all op amps can be treated as ideal op amps. And the consequence of us being allowed to treat this op amp as an ideal op amp is that one, no current will flow into the input terminals of the op amp. And two is that no potential difference or voltage will appear across the terminals. Excuse me, the input terminals of the op amp. So why that's particularly important here is if there's no potential difference between here and here, that means that this node is essentially at ground. So both sides of the piezo element are grounded, which means the SCV term goes away because there is no voltage drop across the device. So we are only left with our motional current that is due to the piezo electric effect. Okay. So all of that motional current is going to wind up flowing through that parallel RC combination. Okay. So from this, we could say that our output voltage as a function of S is going to be equal to negative our motional current times R in parallel with 1 over SC, where 1 over SC is the impedance of our capacitor. So for frequencies where S is significantly greater than 1 over RC, our output voltage will simplify to negative I motional over SC, which is then approximately, so negative S, I'm just going to put it as lowercase e here for the piezoelectric coefficient. So it doesn't matter if I have a longitudinal or transverse configuration. I'm just generalizing things here. So SEAS over SC. Our dependence on S has effectively canceled each other out. And so we're left with negative E A capital S over C, so that our output voltage is effectively independent of frequency. So this is one measurement scheme using a transimpedance amplifier. Effectively, that parallel combination of the resistance and capacitance converts that motional current into a voltage at the output. Another scheme that is commonly used is a voltage measurement scheme. And so for this particular scheme, we might have a situation that looks something like this. So here's our piezo element yet again. I'm going to ground this side. And now I'm going to have a parallel RC network. So let's call this C sub L. And this guy right here will be R. And then our signal here is going to be going into a single-ended amplifier, so some sort of voltage amplifier. And here is our output voltage. So for this particular case, since we're not using a single-ended amplifier, we can't say that our piezo element is simply shorted out on both sides. So we're going to have to deal with our AC current, right? So I'm going to draw these currents in this particular direction just for making Kirchhoff's current law easier to apply. But we have our AC current plus our motional current generated by our piezo element. Again, I'm just drawing them direction down. You'll see why in a moment. I've got my current flowing through my capacitor, and I've got my current flowing through my resistor. And so Kirchhoff's current law tells me that these currents added together need to come out to zero. So I would have IAC plus I motional plus ICL plus IR is equal to zero. If I express IAC as SCV, so let me make some notes over here. So IAC is SCV, okay? IR is literally just V over R. And ICL is going to be SCL times V. Putting all of these three substitutions in and rearranging effectively, we can come up with a relationship. So we would have I motional plus S, the capacitance of our piezo element, plus the capacitance of our capacitor CL, times V, our voltage, plus V divided by R is equal to zero. And then rearranging this guy, we would then find that our voltage at the input of our amplifier, V, is then negative I motional divided by 1 over R plus S C plus CL, which is the same thing as negative I motional times R in parallel with 1 over S C plus CL. So we've got an output voltage that looks fairly similar-ish to what we had over here, right? So we can use a similar approximation, and we can say that when S is much greater than 1 over R times C plus CL, our input voltage to the amplifier is just negative I motional over SC plus CL, or EAS over C plus CL. And then from this, our output voltage is just whatever the voltage gain of our single-ended amplifier is, multiplied by that input voltage V. So this comes out to be, sorry, I missed a negative sign here, negative EAS over C plus CL times the scaling factor of AV. All right. So once again, we have an output voltage that is effectively independent of frequency, and only depends on piezoelectric effects, so how much strain we're seeing. Okay. All right, so these are our piezoelectric measurement schemes. So now let's move on to an entirely different topic and start talking about thermal sensing. And as a background, we are going to have to talk in very simplistic terms about heat transfer. Very simplistic terms for my benefit, not yours, to be really clear here. Okay. So there are four possible mechanisms for heat to move from one point to another. Okay. The first of which is simply thermal conduction. So this is heat transfer through a solid medium. In the presence goodness of a temperature gradient. Then we have natural thermal convection, which is heat transfer from a surface into a stationary body of fluid. Some other notes here really quickly. A temperature gradient in a fluid induces local flow movement through buoyancy and the fluid movement facilitates heat transfer. Our third heat transfer mechanism is forced thermal convection. So this is heat transfer to a body of moving fluid. And I've got a little note here that bulk fluid movement provides enhanced heat transfer. As compared to natural thermal convection. So this should essentially make sense because we're actively adding extra energy in to make the heat transfer happen faster, which is why for those of you that have convection ovens and things like that at home, you typically have to cook things for a smaller amount of time or lower the temperature to get your recipes and all of that kind of stuff right, because it's just constantly dumping heat in more efficiently. Lastly, we've got radiation. So radiative heat transfer is heat transfer through electromagnetic radiation. Propagating in a vacuum or air. All right, so talk about our equations first real quick here. So the governing equations relating the heat transfer rate and the temperature gradients for heat transfer mechanisms are, so let me write this down. So we have Q double prime subscript COND, conduction. So this is what we're going to call our conduction heat flux. It is measured in watts per cubic meter. And this is equal to negative capital K, where capital K is our thermal conductivity. Measured in watts per meter Kelvin. And this thermal conductivity is multiplied by the derivative of temperature, capital T, with respect to position X, meaning we won't have any conductive or conduction heat flux unless we have some sort of temperature gradient across some distance, right? So this is our expression for conduction along a given axis. In this case, it would be the x-axis, but we could do it dt by dy for y, etc., and so forth. Then we're going to have a separate equation. Sorry, that's the G. It should be a Q. Q double prime CONV for convection heat flux. Also measured in watts per meter squared. And this is equal to H, our convective heat temperature coefficient. Let me write that down. Convective heat transfer coefficient, having units of watts per meters squared Kelvin. I'm sorry, what? Yeah, lowercase h. Is my penmanship that shitty today? It is. Look, that looks worse. Lowercase h. That is all it's supposed to be. Sorry. TS minus T infinity, where TS is our surface temperature measured in Kelvin, and T infinity is our fluid temperature, also measured in Kelvin. Okay. The convective heat transfer coefficient is dependent on surface geometry, fluid viscosity, fluid velocity, and thermal diffusivity. And then I've got a little table that I found in a textbook for typical values for H. Yes. Yes. So that is just the temperature. That symbol collectively together is the symbol that I'm using for fluid temperature. So T subscript infinity, that the infinity doesn't mean anything as far as I know. So I'll put a little table over here. Oh, I don't want to do that in red. So natural convection we'll do here. Oh, yes, yes. So I should write that down. Sorry. Fantastic thought there, telling you what the hell this is used for. Natural and forced convection. Sorry, I missed that. And then I'll put the table underneath. Thank you for that correction, Allie. So natural convection, forced convection, here I'm going to do gases, then liquids, once again, gases, then liquids. And then underneath here, I'm going to have convection with a phase change. So this could be boiling or condensation. Okay, so don't have separate thing for gas and liquid because we're in the transition point between those two states of matter. So natural convection, H value is going to be somewhere in the ballpark of 2 to 25 for gases and 50 to 1,000 for liquids. For forced convection, might be 25 to 250 for gases and 100 to 20,000 for liquids. And then for our phase change, typical values are 2,500 to 100,000. And then our last equation, which I'll tuck it in, I'll start it on this next page actually. I'll make sure there's this E is not Young's modulus because of course it isn't. This is our emissive power. Measured in watts per meter squared. This is going to be equal to lowercase epsilon, which is not permittivity. So this is the radiative emissivity where this is effectively a scaling factor that ranges from 0 is less than or equal to epsilon is less than or equal to 1. Then we have this is supposed to be a lowercase Greek sigma, but I'm particularly bad at drawing this letter, so I'm just telling you what it's supposed to be. Lowercase sigma. This guy is what's known as the Stefan Boltzmann constant, which has a value of 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the 4th power. And then lastly, we have T sub R to the 4th power, where T sub R is the absolute temperature of the surface. Measured in Kelvin. And this equation is what will be used for radiation. Okay. So I think this is a little picture from Dr. Kajakari's textbook that I'm going to try to draw really quickly. I found it useful when I was learning this material because my mechanical background is non-existent. So I never had to do literally anything with heat transfer at all at any point in electrical engineering. Maybe I did in thermo, I just wasn't paying enough attention. But anyway, so this kind of helped me figure out what the different things were, okay? So I'm going to attempt to draw a pot of boiling water. So here is my cross-sectional view of my pot. And then I've got water inside said pot. And then down here below, we make those slightly different colors so we can see the difference better. This is my heating coil down here. Which has some temperature, which I'm going to call T coil. Okay. So let's talk about the different heat transfer methods that we are going to see in this thing. Okay. So here in region 1, I'm going to see simple conduction, right? So I have a hot surface from my heating coil directly touching my pot. So I'm going to have simple thermal conduction as a heat transfer mechanism between my heating elements and the pot itself. Okay. I'm going to have some convection from the solid surface of the pot to the liquid or water material, so my fluid. So I have heat transfer from a surface to a fluid, so I have convection. I'm also going to have convection from liquid to air. So once again, I have a surface and then I have a fluid because air is just as much of a fluid as the water is. So I've got convection there. I'm going to have convection from the solid pot wall to air here. And then I'm also going to have radiation from these hot surfaces into the air. If I, a lot of you guys probably work in the labs over in the IFM biomedical engineering building, things like that. You guys probably have hot plates. Does your hot plate have a magnetic stir bar? Forced convection. Boom. There we go. Okay, so that's really all the difference is. Yeah. So heat transfer occurs whenever a temperature gradient exists. The ability of a medium to object to heat transfer between 2 points is typically quantified by its thermal resistance, where the greater the thermal resistance between 2 points is, the smaller the heat transfer rate will be under a given temperature difference. So if we had a simple longitudinal rod having some length L, some cross-sectional area A, like so, and let's say that there was some temperature difference between the ends of this rod that we will just call delta T. There is our thermal gradient. Based on these parameters, the total heat flow due to conduction is going to be simply our, let me double check what I called it here, but I believe it was, yeah, conduction heat flux. Q conduction double prime multiplied by our cross-sectional area. So this would be negative K times our cross-sectional area times the temperature gradient over the length of our rod. Okay. So we can define our thermal resistance RTH as simply the ratio of our temperature gradient divided by our heat flow due to conduction. Okay. And so this is going to come out to be 1 over K times the length over the area. And this is known as thermal resistance because it looks incredibly similar to our normal electrical resistance formula. R is equal to either rho E L over A, which is how we've learned it in this class. But some of us probably know that the inverse of rho is where rho is the resistivity, is the conductivity. So this could be written as 1 over sigma sub E L over A. So this is our electrical conductivity that we use to calculate resistance. This is our thermal conductivity that we use to calculate heat flow. So it has the same form as resistance. So we get to treat it like a resistor, which is great because I'm an electrical engineer and resistors are easy. Okay. So let's work an example here. So let's say that we have a resistive ohmic heater is located in the center of a suspended fixed cantilever beam. So that might look something like this. So as a top view, of this overall profile. So this is our substrate. I'm going to put in a note here. It's effectively acting as a heat sink. And then we've got this beam profile across it. And then I'll do this in pink just so that it's obvious. This pink is going to be metal. So I've got a metal strip here, a metal strip here, and then connecting these two metal strips is a simple ohmic heater, which is typically going to be made as like a serpentine section of metal. The reason why it's a serpentine section of metal is so that we can have a very long length with a very long cross-section, or excuse me, a very small cross-sectional area, so that when we push current through it, it heats up a lot because the resistance is very large. Okay. So this thing right here is our heater, and then this guy right here is just a strip of metal. From a side view, let me write this down. Top view over here as side view. We might have something like this. So we've got our beam. And let's say that the width of the beam is 10 microns. and the thickness of the beam is 0.2 microns. And then here over the top, we have our metal. Where the width of our metal is, 8 microns. And the thickness of our metal is 0.2 microns. Give you guys some more information here. Didn't realize I was running out of room, but that's okay. The beam is made of silicon nitride, which has a thermal conductivity of 5 watts per meter Kelvin. And the metal leads are made of aluminum, which has a coefficient of 240 watts per meter Kelvin. I've got the beam is 10 microns wide. So this length, let's put this on here. The length of the beam is 100 microns long. The input, sorry, this is taking forever to set up. The input power to the heater is 0.1 milliwatts. And we want to know what is the heater temp assuming the substrate maintains a temperature of 27 degrees Celsius. Okay, so let's start by finding the thermal resistance of some of the different things here, okay? So for our beam, let's do that one first. The thermal resistance of the beam. So that is 1 over K for the beam times the length of the beam over the cross-sectional area of the beam, which would be the width times the thickness. So that's fairly straightforward, right? So 1 over K is going to be a meter Kelvin per 5 watts. So literally just the reciprocal of that guy right there. We have our beam length of 100 micron. And then we have our width of 10 micron and our thickness of 0.2 micron. And so this comes out to be 1.0 times 10 to the 7 kelvins per watt. Then we have the thermal resistance of our metal strip. I'm sorry. I have an error in my drawing here. I need to fix really quickly. This is the length of my beam. So I've got a length of beam on both sides. I couldn't read my chicken scratch. My apologies for that. But that guy is the 100 microns. So for my metal strip, I've got a similar length there. So that's going to be 1 over km times the length of the metal over the width of the metal times the thickness of the metal. So effectively, it's the exact same expression, except that I'm going to use that meters, Kelvin, 240 watts down here. And then everything else is the same, except my width is 8 microns instead of 10 microns. And this comes out to be 2.604 times 10 to the 5 kelvins per watt. So hopefully, as expected, the thermal resistance of the metal is significantly less than the thermal resistance of the beam, because the whole point of the metal strip is to conduct the heat better than the beam itself. So having these values, what would the net thermal resistance of our system look like? Okay. So I'm going to draw this as kind of a circuit, okay? So on the top is my heater, and on the bottom is my substrate, right? So the heater, is that the chemistry lecture hall above us? They're moving furniture, maybe? I don't know. Anyway, okay, so the reason why I'm drawing the heater at the top and the substrate at the bottom is because the heater is the highest point in temperature in my system, and the substrate is the lowest point in temperature in my system. And so when I draw circuits, I typically try to draw things highest electrical potential at the top, lowest electrical potential at the bottom. So I'm doing highest heat at top, highest heat at bottom. So I believe that going from my heater to my substrate, I have a thermal resistance of, let's say, the beam on the left, right? So this is going to be an RB. I also have a thermal resistance of the metal strip on the left. Then I have the thermal resistance of the metal strip on the right. And lastly, the thermal resistance of the beam on the right. So effectively, I just have those 4 paths for heat to transfer, all connected in parallel between my heater and my substrate or heat sink. Okay. So from this, my equivalent thermal resistance is simply going to be twice Rm plus twice over Rb to the -1 power. So that's just equation for 4 things in parallel, treating it exactly like they were resistors. And so I would have an equivalent thermal resistance of 1.269 times 10 to the 5 kelvins per watt. The temperature of my heater could then be found to be whatever the temperature of my substrate is, plus my equivalent thermal resistance times the power that's being absorbed by my heater. And so this comes out to be 27 degrees Kelvin plus that 1.269 times 10 to the 5 kelvins per watts times 0.1 milliwatts comes out to be 39.69 degrees Celsius, where I guess realistically here, I should change that Kelvin to a degrees C because Kelvin and C are the same temperature scale, so I don't need to do any real conversion there. My change in temperature then, delta T, was 12.69 degrees C or 12.69 kelvins, assuming that we didn't lose any heat to radiation or convection to the air. All right, so one last little thing and then we'll wrap up for today. This is still on the basics of heat transfer. In many devices, the speed at which the temperature of a microstructure can change is important, okay? And the thermal resistance influences the response speed of a thermal system. So let me write this down right here. The relationship between stored thermal energy and temperature change is Q, where this is my thermal energy measured in joules, is equal to, I'm going to have this as SH, which stands for specific heat, measured in joules per kilogram degree Kelvin. Then I have my mass measured in kilograms multiplied by my temperature gradient. And you may also see this as CTH, where this quantity CTH is my heat capacity measured in joules per Kelvin times my difference in temperature. So this heat capacity thing is also at least interesting to me as an electrical engineer. So capital Q is our thermal energy, right? We've been using lowercase q to talk about charge, right? So if we relate those two quantities to each other analogously, treating thermal energy as if it were charge and delta T as if it were a voltage, then that heat capacity is effectively playing the role of capacitance in that analogous electrical system. So essentially, we could say that tau, this is the time constant. Make a note. For heating slash cooling a structure is equal to the thermal resistance multiplied by the heat capacity. So it's literally the exact same time constant as an analogous RC circuit. All right, that is enough terrible explanation of heat transfer from an electrical engineer for today. So what we're going to talk about on Friday, pardon me, my nose is itching, is we're going to actually look at a particular sensor called a thermal bimorph. The math involved with that is kind of gross looking. Once we do that, we'll be done on Friday. So we'll probably knock off about 30 minutes early or so. All right. Thank you for putting up with my bullshit.